Good afternoon, everyone, and welcome to today's SimScale webinar. My name is David. I'm co-founder and CEO of SimScale, and I'm very excited about this session today, and I'm glad that so many people could make it and are interested in what we're up to and in the news that we're sharing today. Before we get started, a few technical notes. We're using GoToWebinar to stream the session, and it provides the option to ask questions at any point during the session today. So whenever I'm rambling or you don't understand something I'm saying, or I'm saying wrong things, you can just type it in and ask questions about it. I'm pretty sure the session today is pretty packed, so we might not be able to get through everything, through all the questions, but I'll try to at least cover a few by the end of the session. That being said, there's also a recording of the webinar today, and we'll put it on YouTube later, and everybody in this session also will get simply the link to this YouTube video. So without further ado, what we're going to talk about today is a new partnership that we're announcing here at SimScale. We partnered with Numeric Systems, also based here in Munich, to deliver a new type of solver called Pacefish via SimScale. We're going to see that later in action, but that's what we're going to talk today. But before we do that, let's quickly make a step back and sort of why, right? Why are we doing this? Why are we talking about a new solver on SimScale, or why did we do that? And this shows sort of over the past couple of months the simulation jobs that were carried out on SimScale. So it's fair to say that we're seeing on a weekly basis, on a daily basis, new applications, projects, companies that are interested in using simulation in their design processes, and hence we see a ton of these, right, and a ton of different requirements, and we got better at understanding which do we see regularly, and we use all of these insights to sort of drive the product decisions, the product development decisions at SimScale. And so as today, the audience is mixed today, right? There's a couple of existing SimScale customers, and then a couple of folks that are interested in what we're doing. But as the existing customers know, we address most of this with on our production system, currently on production, with a finite element solver and a finite volume solver for CFD, a finite element solver for structural, and some of the conductive heat transfer things we provide. And the CFD parts we address with OpenFOAM, a finite volume solver, right? And this is here to stay, and we continue to invest in it, and we're, definitely not done here, right? There's a lot we need to integrate, a lot to improve, a lot of pre and post processing to enhance. So we continue to invest here, but the time felt right to now announce a new partnership, because what we've been constantly doing is screening the market and talking with different folks in this industry to see what type of new solvers are available, what type of new technology would make sense to help our customers be more successful. And one thing we regularly saw is the need, and we're going to talk about in a second in which applications exactly, is the need for aerodynamics analysis that's transient yet fast, right? That provides turnaround times that are faster than what we can achieve with finite volume-based CFD. And this was really sort of the initial spark to partner up with Numeric Systems and deliver a GPU-based Lattice Boltzmann solver that we're going to talk about in a second. This is sort of the background to this story. Before we move on, we are also already working on the next ones, right? So there's more partnerships to be announced, more solvers to be integrated in SimScale. So you're going to hear us talking more about new solver technologies in the next couple of months. But now, without further ado, let's talk about Pacefish. It's a development from our partner, Numeric Systems, also based here in Germany, in Munich. And in subsequent webinars and subsequent blog posts and content we're going to put out, we're going to talk much more about this, and we have also them explaining more about the solvers and the inner works. So today is really just a very top-level information or introduction to what this is about. It fundamentally uses the Lattice Boltzmann method as opposed to the finite volume method that is used by OpenFOAM. It runs multi-GPU, so it doesn't run on just one GPU, but since we're running in the cloud, right, we're firing up large GPU instances, and we're running the code then in parallel on multiple GPUs, and the problem is distributed across them. You're going to see in a second, or already on that animation, right, that it's fully integrated into SimScale, so it looks and feels almost, we're working on it, but almost the same as with the other CFD capabilities we provide. So it comes with a very similar workflow, I guess. That being said, it comes with a variety of turbulence models enabling high quality or high fidelity aerodynamics analysis, and we're going to talk about them later as well and dig a bit into that. But that's definitely, I guess, a secret sauce or a special ingredient of Pacefish. That being said, what can you do with it, right? There's a lot of practitioners in the session today. So, what's in it for you, right? Why should I care? In the initial release, what it will be able to do, what it's targeted at, is really the AEC industry, right? And you can see that on the top. We can see on the top left a building wind load predicted. That's a nasty several-story high-rise building in a coastal region. Here in the top right, we can see a whole city being analyzed for pedestrian wind comfort. And a few words on this. What we've seen, right? We've been very successful in the AEC industry and are growing fast over a number of applications in that industry. So talking about HVAC analyses, passive ventilation of buildings and these sorts of things. And one aspect was all the time wind loads, right? Wind loading on these structures, specifically when the structure is not, a small building or a short building, but structures that are either very slender or, bridges or high-rise structures, or at times we also saw smaller houses or structures, but that are in a coastal area where wind loads are very hard to predict. Long story short, in all of these situations, what you really want to do is transient CFD, because you're not primarily interested in, the average steady state wind load on it, but what you're actually interested in is the vortex shedding, the transient effects of the flow. And we've done that in the past also with finite volume-based solvers, but it's really tough to make that economically work, right? We looked at times, if you want to use an LES turbulence model, we looked at computing times of, at times weeks, right? And in some situations that works, in others, it's tough to economically justify that. And so we've been always on the lookout for a solver that's able to provide the fidelity, the accuracy that the wind engineer needs, but at the same time provides a much faster turnaround time, right? And that's what led to Pacefish. At the bottom, you can see some other applications that are already possible, but the initial feature set is really a minimum viable version specifically targeted at aerodynamics of buildings. On the right, a couple of more details to that. All right. A lot of talk, a lot of slides, so I suggest we take a look at how does that look in action. And for that, we quickly hop over. Again, for the folks in the audience today that do not yet have a SimScale account, simscale.com, it gives you, let's quickly do that. Right? You go to simscale.com. It's completely web-based, so you do not need any local hardware, local software. You do need a computer, right, to run a browser on, but everything you need is a browser and an internet connection. And on the top right, if you're not logged in, you can sign up. It takes you a minute, and then you can give this a spin yourself, and don't take my word for it, right? Once you've created a project in SimScale, this is what it looks like, right? And now what I'll do is I will just show you a super quick walkthrough, right, to get a feeling for how this works and how this feels, and for you to make a first judgment whether or not this would be helpful for your work. We'll not dig into the details of turbulence theory or the inner workings of Pacefish. It's really just a first introduction to that. So what we're looking here at is a city plan, a couple of buildings in here, and I'm interested in pedestrian comfort. For the people that have worked with SimScale, you can see that the user interface looks almost the same. What you note is that there is no mesh, right? For Pacefish, you don't generate a mesh. It's being implicitly generated. And so just looking at the most important things, so what we would do is we would define a virtual wind tunnel. So this is the area in which we want to compute velocity, pressure, and the likes. We define a material, in that case air. We define a velocity inlet, right, 20 meters per second. And here I could now upload turbulence, a turbulent profile or an atmospheric boundary layer profile, these sorts of things. All of this is possible. We define outlet, sides, we structure our wind tunnel, that's it. So just very simple boundary conditions. Also the initial set of boundary conditions is really targeted at external aerodynamics analysis. So that's what it's built for in the initial release. Next, we say, okay, how many seconds do we want to compute this? As always, I can set a limit. I don't want the cloud to go crazy in case something goes wrong. I have a similar set of result control items that I'm also used as a SimScale customer from the other solvers. So I can define, forces and moments. I want to compute the force on a specific building maybe, or I have some pro points, some locations where I want to put something in, these sorts of things. Furthermore, anything else? Yeah. The rest maybe a bit very detailed. Then I can steer the lattice resolution. So again, we won't go into the details here, but I can drive the resolution of the mesh depending on which areas of interest, which is not. I have the ability to locally refine on topology of the model, also driven by geometric primitives. Again, same story as with the other solvers in SimScale. And then I run it, right? Let's take a look. And I'm going to show you later sort of how you can drive fineness, etc. So I won't go into the details here, but I just want you to once show you this end-to-end. All right. All right. And what we're now looking at is really on the pedestrian level, right? This is what? Let's make this a bit nicer. On the pedestrian level, I think it's 1.6 meters. Yeah, a slice plot of the velocity, right? And so I can look at the different velocity increases between buildings. I can identify Venturi effects. I could now run a design study whether or not different rotations of my building would lead to a better wind behavior inside the city, these sorts of things, right? And all of this basically end-to-end in a web browser. And the interesting piece here now is, let's quickly pop this over, that we ran 200 seconds real time, right, on a grid of 15 million cells in under 60 seconds, right? And we're going to look later at a couple of performance metrics as well. The beauty of this is really that I can run transient analysis, highly resolved. Honestly, I wouldn't call 15 million cells now highly resolved, right? So we could just bump this up in a very short amount of time. So the ability to quickly run high fidelity flow simulations accurately in a short turnaround times is just something that's super helpful in these scenarios for folks in the wind engineering industry. All right, before we jump off, let me quickly kick off before we jump back to the slides. 1 second. All right. Let's pop back to the slides, and we're going to look later at this project again, right? What I didn't show is the ability also, you can animate it. You can see it here, right? Now it's clicked on animate. So all of these are transient results. So an unsteady flow, and now you can see, right, how the air is moving through the city, and you capture all of these transient effects in there. All right. I hope this got a first feeling for sort of how this looks like, how does the workflow look like, how fundamentally the integration of Pacefish into SimScale works. What we want to talk about today as well, and why we're so excited about this partnership, is also what makes Pacefish unique, right? What makes this solver unique compared to others. And if you break it down to the essentials, it's three things. The first is it enables highly accurate analyses, right? It's not something, where you get a rough number, where you get a rough result, but it has the capability, if you resolve it fine enough, your domain to predict it very accurately. And again, we're going to look at this, right? We're going to look at a few validations in a second. But it comes from this unique combination of, on SimScale, you can run it up to, we ran cases up to 400 million cells on it in the browser, right? So you have this massive scale because it does multi-GPU, and at the same time, it has this sophisticated turbulence modeling that allows you to predict aerodynamics very accurately. The second piece is fast. We'll have more content later on explaining this in more detail, why it is fast, right, and why does it make it so fast. But it's this unique combination of the Lattice Boltzmann method that's just almost, it's very well suited for an implementation on a massively parallel architecture on GPUs. And so taking advantage of this new the GPU compute platform in combination with this method allows these unparalleled turnaround times of simulations, even on a massive scale. Last but not least, the beauty again of this method is that even if you bring in nasty CAD, right, we're going to look at an example later, you bring in nasty CAD, dirty CAD, not well prepared CAD, which we all know that, right, which is simply the reality of being an engineer that does CFD. It deals with it gracefully, meaning that it doesn't resolve all the nasty stuff, right? It doesn't necessarily predict the flow around all of this, but in case of doubt, it'll just ignore it. Right? We're going to see that in a second in more detail. And that makes it very easy to deal with and a very user-friendly way to set up these problems. One quick jump back to just quickly to the post-pro. So this buffered now, right? And this is an animation. This was the flow field we looked at. So we can see actually, okay, the flow is moving through here. I can interact with it. The rendering is done on my local computers. I can have a fast interaction with this. All right. Now I guess everyone making a living from selling simulation software says, their simulation software is great. So I guess it's time to back these statements up here with a little bit more data, with a little bit more content behind it. So let's do that. Let's cover all of these three aspects a bit more in detail. The first thing, let's take a look at its accuracy, right, and get a feeling for how accurate this is. Three example projects today, and to manage expectations, we just will touch very briefly on them. We won't go into the details of them. Why? Because the beauty of SimScale is that all of this is online, right? I'm going to show you that you can just follow a link, and you can open up the exact definition, all the results, and just visualize all of this in a browser, right? So you can do that yourself. There's more documentation for each of these projects. So today we're just going to get an overview, and if somebody of you is interested here, I would recommend following on with going to these public projects. All of them are publicly available. You only need a free SimScale account, and you can take a look at them. We'll first take a look at this rather academic example of the cylinder. Afterwards, the Ahmed buddy from the automotive sector, and then last but not least, the one what we're targeting at the moment is the AEC sector. I guess everybody in the audience that has some heard some class on CFD probably has seen this this problem. Flow around a cylinder. What we compared it with is obviously experimental data from the papers mentioned below here. And then, because we ran this case obviously already with a finite volume method, with OpenFOAM and an LES turbulence model, we basically just updated that project with new Pacefish results. And what we're looking at is on the left, I think, again, nothing special about it, right? Rather, we can see that the instantaneous flow field captures these vortices that are being formed behind the structure. And on the right, we can see a plot of the pressure coefficient in circumferential direction. So this is in front of the cylinder, and then in 100 degrees, right, how the pressure coefficient over the cylinder develops. Now we would need to talk about, what grid was used, what turbulence model was used, how resolved was it, etc. And again, I would encourage you to not take my word for it, right? You can just, this is a public project, right? You can follow this, and you can, oh no, damn it. Okay, my apologies, it's the wrong link. Let's quickly search for it, but it should be easy to find. I hope so. So these are the public projects of SimScale. So we'll search for a cylinder. Let's see if this works. This wasn't practiced that way. My colleague Trupan ran this, so we search for his username. There you go. This should be it. Nope, that's still the Ahmed body. Last try here. There's the cylinder. There we go. So here you can open up the project in the SimScale workbench. You can take a look at the exact details, right? You can look at the results, references, etc. So I would really encourage you to, if you want to dig into this, right? How was this exactly done? What type of grid resolution was used, etc. I definitely encourage you to take a closer look. But I think fundamentally we can see that we're very close to experimental data, and also on the accuracy level of a finite volume method there. Same Ahmed body, again, not a lot of introduction here. I think everybody familiar with CFD or that has looked into that knows the Ahmed body. Just quickly, that you have seen this geometry. So a geometry close to a car where we have an external flow around, and what we're interested in is the drag coefficient of that car. We can see on the left a qualitative comparison of the vortex structure behind the body. On the right, total drag coefficient predicted, experimental data, and then a bunch of other models, other solvers from the literature mentioned here at the bottom. Also here, if I'm correct, I think that's around about 7% close to the experimental value. So again, the point to come across here is that it's not sort of, colorful picture kind of CFD. It enables you to highly resolve a domain, a problem, and then accurately predict aerodynamics of it. All right, and then the last example, and I guess the one on which we will spend most of the time here, is a experimental validation of the flow around a high-rise building. So we can see here on the left, very simplified building with all of the red points indicate measurement points from the wind tunnel. You can see the literature at the bottom here where different measurement techniques were benchmarked against each other. So the paper contains two different techniques, how the pressure was measured at these different points, and they provide both of these methods. We're going to see it in a second. And we can see that I think it's 180 points or 150. We have pressure values measured. And on the right, you can see an arguably very fancy simulation of what we ran from it. So we ran this analysis with Pacefish, rotating this building, right? So running the wind from various angles and then measuring the moment it creates on the building and comparing that with wind tunnel data. So on the left, again, what we expect, we can see an average flow field at the bottom, an instantaneous, transient, or unsteady flow snapshot, if you will, of the velocity field at the top. Oh, and the color scale is missing. Apologies for that. And on the right, the more interesting piece is we can see over the degrees, the 90 degrees of which we rotate the building, the different overturn moments that are acting on the building as a result of the pressure that's acting on the building. So at the top, we can see, let's go quickly back, right? So overturn moment for X is in that direction, overturn momentum in Y is in that direction, and then the Z moment is a torsional moment. And so we're looking at X moment at the top, Y moment in the middle, torsion moment at the bottom. X-axis shows the different degrees, the different rotatings of the building, and you can see that the black line is the computations done with Pacefish with this Lattice Boltzmann method, and red and blue are the two different measurement methods used in the wind tunnel in that paper. And so we can see again that we're predicting the total overturn moment very more close to what was measured in the wind tunnel, both for the X moment and the Y moment, and same goes for the torsion moment. One could argue now here, right, we have sort of our simulation point here is very much in the middle of the experimental data, so we're already running that in an extended version and going to include more of these angles. But bottom line, well agreed with wind tunnel tests of this building, very close correlation here. Also here, I'd encourage you to, let's quickly hop over. This is a public project. This view you can even see without having a SimScale account, right? Just to open the project, you need a SimScale account. And you can see a lot of documentation, more details on the grid, also specifically more details on, we also have analysis of each individual point, because it's always very interesting how a solver behaves on the backside of the building, in the etc. So there's a lot of more content here. And I encourage you to, if you're interested in this, take a look at it. It's just tough to put this into a short webinar. To drive this point home, what we looked at is 3 different cases where an aerodynamics experimental data has been validated with Pacefish. We're seeing good agreement here, right? The devil is in the details. And again, I'd encourage you to take a look at the more detailed setup. Good. So much for accurate, right? A couple of more data points why we think this is accurate. Let's talk about speed. We call it fast, right? What is fast, or why fast? Again, everybody that has done benchmarks and CFD knows that, there's so many factors to look at. There's so many different things to look at. It's always tough to break it down on one number or one chart. So I'll just try to give you one example here. How fast it is and whether or not it outperforms another method is, as always, dependent on the specific project, depending on the specific physics. There's no one size fits all. But we wanted to give an indication of the speedups we've seen for these specific projects, right? The applications where we've seen success with is where a transient aerodynamics phenomenon shall be predicted. And this is oftentimes, vortex shedding on slender structures. And this is here an example here. So we have another building case, slightly different geometry, and we're looking at, again, same story, we're looking at different measurement points across the building. It's not about validation, so we can see here as well, okay, we've validated it against experimental data. We can see that we, on all sides of the building, were in correlation with the experimental data. What's obvious is on the windward side, it's definitely much more accurate than on the other side, where in the wake, which is again to be expected. Everybody in CFD knows that this is where the magic happens. And but overall, good agreement. So accurate results. And the amazing thing is here that in that specific setup, right, where we ran a 2 million finite volume cell mesh against a 15 million lattice Pacefish mesh, we can see that, it's a speed up roughly of 30, right? Again, if you would tune some numerical settings, if you would tune maybe the machine, the grid size, these numbers might vary, but overall, we can see a fundamental speed up, a fundamentally faster turnaround times of such aerodynamics analysis, which is great, right? Which is specifically, which makes it very compelling and very interesting for these types of analysis. Also, this is available as a public project, so again, I'd encourage you to take a look. So much for speed. Now let's talk about robust. We said the third interesting property about that solver is robustness. Okay, what do we mean with it, right? This is an example geometry of a city plan. Let's take a closer look at this, right? There's all sorts of nasty stuff in here. Here we can see 2 solids that are significantly overlapping. Over there we see an arguably complex surface model. And it gets even trickier. Here we can see a sliver face on this very nasty surface model. Right? And there's more of that in there. Right? Again, here we have not just overlapping, but intersecting stuff, etc. So while this is a NURBS model, I think it's a step. I think it was brought in as a step. I'm not entirely sure. But while this is a NURBS model, there's all sorts of challenges when it comes to meshing this. Right? I think there's different measures and different strategies. but it's definitely not something you would be excited of now meshing with a standard mesher, a body fitted mesher. And now, what's great about the Lattice Boltzmann method, or this implementation about the Lattice Boltzmann method, is that you can really drop this in as is, right? And again, let's take a look at this, whether or not this is actually true, what I'm saying. I'm quickly hopping over. Where are we? Let's quickly open this up. All right, this was the model we looked at in the beginning, right? So let's take a closer look. So this is really in there, right? It's not like that I ran a sort of a simplified model. So this is there, right? We go over here. Let's zoom in here. There we go. Right? So this is this phase I was talking about, etc. Right? Arguably, I've seen nastier models, but we all know the reality, right? We're using at times. This stems from the fact that the civil engineer or the wind engineer is working with somebody else with a third-party CAD system, so he doesn't have clean CAD to start with, and then from there it only gets worse, right? So the challenge of dirty CAD to simulate is just real in every practical use case. And so in this scenario, I really ran it end-to-end, just dropping this in, right? And I think the important piece to understand, let's take a look. Which one will we open up? Let's open it up very coarse, right? What we mean with gracefully dealing with this is that you basically, a grid is put into this, and you have this staircase at the surfaces, and so at times, stuff might just not be resolved, right? In this case, we didn't resolve this small detail here, right? So it's just ignored, right? Which is fine, because I can just drive it from there and see, okay, this is not resolved, and I, as an engineer, can decide whether or not this is fine if it's not resolved, or if I want to resolve it. And if I want to resolve it, you're free to do so. You just throw in more cells. You have access to multi-GPU instances, so you can run this on a much finer scale, right? The beauty of this is that you have this, you avoid the challenges of the mesher failing or the solver diverging because you have nasty cells, or you have nasty, I don't know, cells that are not good for the solver can handle these sorts of things. So that doesn't mean that, oh, it can deal with everything and it's accurate no matter what. No, it's not, right? You get what you throw cells in, but it allows you to do that in a very easy and in a very fast way, which ultimately saves you time as an engineer. So let's quickly open this one up, right? This is a finer resolution, just to compare. The last time step. There we go. And not show element mesh. All right. And again, here I can see I resolved the model now. I resolved the flow channels with a much finer grid, so I can expect to capture all flow phenomena in more detail. As I said, you can drive that locally. You can drive local refinements, etc., to capture what you truly want to capture. But fundamentally, it's a very graceful way of dealing with dirty CAD, of dealing with complex CAD. And I think I have a slide to this as well, showing this side by side. Yeah, there you go. Right, this is what we just looked at. Right, on the right, a coarse lattice, on the left, a finer one. Zooming into interesting regions here, we can see that this specific area in the middle of that city plan is much finer resolved on the left. So on the right, I have some artificial blockage because I don't resolve the flow channel fine enough. And ultimately, this is also what I will see in the resulting flow field, right? So on the right, you can see in these small passages here, much or significantly smaller speeds than on the left, right? And I can just drive that without going to my CAD and cleaning stuff up and working with Mesher. I can just drive it from saying, okay, hey, I want to resolve this, and the solver always deals gracefully with it, and so it gives me a much better experience while being in such a project. All right. we're almost towards the end of this session. As a quick wrap-up, this new solver is now available, right? We're working already with customers with it, and if you're interested in it, I'd encourage you to reach out to us. We're running multiple demo projects. We're running different benchmarks with folks interested in that. So I'd encourage you to reach out if this sounded like something that could be actually interesting to your work. If you're interested in accurate, fast, and robust solver for aerodynamics analysis, do let us know, and we'd love to talk about it. And with that, we're through with the official part of the webinar. We shot for 30 minutes. Took a bit longer. Let's see if there's any urgent questions that we can answer at this point, or if I just talked way too much and everybody is lost. So a few, yeah, good questions already popping in. Okay, I'll try to cover a few of them, but we definitely can't cover all of them. A couple of them, and some of them are super long, so I would really encourage you. My email address is also in the description of that webinar. Reach out. I'll make sure either I can answer it or I'll connect you with a colleague on our end, and that can answer it. So I definitely encourage you, if we don't cover it today, do reach out. One audience member asks, just checking isothermal. Yes, correct. In the initial release. Oh my God, that's going to take too long. In the initial release, it's an isothermal. It only solves isothermal aerodynamics. So you can't do any convective heat transfer goodness. Can't be looked at. Any buoyancy effects can't be looked at. As always, we're very much looking for our customers, folks interested in working with SimScale, for these requirements. And we have it already multiple times. But as of now, what's currently available, isothermal, yes. And yeah, no convective heat transfer analysis. One audience member asks whether or not post-processing is using GPUs. Yes, yeah, it does. I think the detailed answer would need to come from somebody from our pre and post-processing team. But in a nutshell, there's a combination between GPUs being used in the cloud, right? So remote, server side, as well as for the interactivity client-side rendering. So what you saw, let's see if it's still open. It's probably not open anymore. It's always my luck in these demos. No. So what you saw is this level of interactivity. Oh, there you go. Right, this level of interactivity. This is now client side. Right? So these triangles are really on my local GPUs, but there's specific preparation steps that have been done before. Also here another question going into the direction of what can I do? What can I not do with it? One question is, can it only be used in a wind tunnel situation, an external flow? As of now, so the fundamental method, obviously not, right? That's on the horizon, that this will be possible also internally. And we already ran benchmarks and tests with it. But in the initial implementation inside SimScale, yes, it's being built for external aerodynamics. So this is the current workflow, current limitation. And it also comes from the question comes from an existing customer. So this is also the situation that, or a difference in, there's a few differences still in the workflow of this Lattice Boltzmann solver versus the other solvers in SimScale, and this is one of them. Some audience member commented that it was a dense but good presentation. Thanks a lot. Yeah, I always talk way too fast, so I'm sorry for that. I should have apologized in advance, but thanks. One user asked, how high can the geometric complexity be to solve it? And I think that still can be solved. And I tried to give a notion for it that ultimately, if you do not resolve geometric features with your lattice, with your mesh you're using here, you won't see it affecting the flow results, right? So the answer is, I guess, twofold. I mean, again, the solver doesn't care about complexity, or the workflow doesn't care about complexity. But to resolve super fine granular or multi-scale geometry, if you will, with a lot of small features while having a large domain, you will need cells, right? You will need voxels in there. And I guess this is, again, this powerful combination between this method and being available on large GPU instances in the cloud. So you do not need an 8 GPU instance on your local desktop. You could just leverage this via SimScale. One audience member asks whether or not the grid is uniform, or if I can bring in a finer mesh in a specific region. You can absolutely do that, right? Let's quickly take a look. I mean, this is available on SimScale, right? This is the cylinder project, where you can see that, driven by geometrical primitives around the geometry of interest, we drive different fineness levels, right? You can also drive that from the geometry. So you could say, you know, this specific building, I want to have a bunch of cells around it, inflated, that I nail my Y plus, these sorts of things. So you can absolutely drive the mesh dependency. Okay, two more. I think those are small ones and can be answered quickly. One question is, does this LBM solver actually solve two-phase flows? Right now, no, it does not, right? It has really been built for aerodynamics, and this is what it does. So this is the initial go-to-market. Again, I would encourage everyone to, there's multi-phase flow solvers in SimScale, right? Finite volume-based, so you can run multi-phase flow analysis on SimScale, but with this specific Lattice Boltzmann method, you cannot right now. Last question, and then I guess I suggest we wrap it up there, and I'll try to cover the rest of the questions by email or in subsequent conversations. Last question is whether or not this is, this solver is the only solver available on SimScale, and it is not, right? Let me quickly, again, demo this, not really again, just quickly showing it to you how this would work. So if I open this up, and what we looked at, right, is we all the time looked at this geometry, right? If for whatever reason I'm saying, okay, hey, this geometry, I actually now want to run it with a finite volume method, right, or another solver, or I want to run a passive ventilation scenario of this one where I really want to see buoyancy effects in there, right? Then in that case, I would just kick off another simulation, right? I would just go with the normal incompressible, not the LBM, and now I just said we wanted to run a convective heat transfer analysis. So obviously I would run a convective heat transfer analysis, right? So I would choose this one, and now this in the back end would use a finite volume method, OpenFOAM, to run this analysis, right? So this is really how that all of this is integrated within one user interface, that you have access to all of this functionality. All right, that being said, I hope this was interesting and relevant to you, and it made sense that you carved out this time from your day. I very much appreciate the time. Love to, if you're interested in that, learning more, testing it yourself, I'd really encourage you to reach out. Would love to have a conversation. And with that, I wish all of you a good evening, and see you next time. Bye-bye.